Hello everyone, my name is Sanjeev Gorbole and I'm excited to present my final project for this course, Franka Warehouse Manager. This project implements a human in the loop industrial automation work cell designed to bridge the gap between autonomous robotics and human quality assurance. The motivation for this system stems from a real world bottleneck in logistics, where robots are incredibly efficient at repetitive pick and place tasks. They often struggle with subjective quality decisions, for example, deciding if a scratched surface is acceptable or damaged. On the other hand, manual sorting by humans is slow and ergonomically dangerous. I designed this system with three stakeholders in my mind. First, the factory manager who prioritizes throughput and inventory tracking. Second, the quality control operator who needs a safe remote interface to make decisions without entering the robot's workspace. And third, system integrator who requires a robust software architecture that won't crash under test. My solution uses the Franka Panda robot to handle heavy lifting while providing a remote graphical user interface for a human to make the final sorting decision. To achieve this, I completed four major technical tasks. First, the environmental design. Rather than relying on static mesh files, I utilized procedural generation within the code. I constructed a realistic conveyor belt system using geometric primitives, a rubber black belt surface, polished steel rollers, and safety orange guardrails. This required precision calibration as placing the belt on a height of zero point 0.4 meters meant retuning the robot's grasp parameters to avoid collision. Second was the manipulation logic. I moved beyond simple point to point movement. This robot executes a complex state machine. It performs a linear scan using Cartesian path planning to simulate reading a barcode. It utilizes a retry logic loop, attempting to three different gap solutions if the inverse kinematic solver fails. Finally, it brings the object to a custom quality control station, a camera assembled assembly I model in the simulation aligning the object specifically with the lens for the inspection. Third, the graphical user interface. I developed a full dashboard using Python's Tkinter library. This GUI replaces the command line offering a real-time status bar, a dynamic inventory grid where buttons disable automatically to prevent race conditions, and a decision panel that only unlocks when the robot is ready for the human input. Finally, the creative component. I implemented and simulated computer vision, a backend database where it assigns a hidden defects at crates when they spawn. The system reveals this data only when the robot presents the item to the camera station. Moving on, core challenges. Early in development, the application suffered from critical crashes known as X11 bad length errors. This happened because tkinter runs on the main thread while ROS callbacks and move it commands run on background threads. When the robot tried to update a GUI level directly, it corrupted the memory. To solve this, I engineered a procedure consumer architecture as seen in the diagram. The backend robot logic acts as a producer instead of touching the GUI. It puts messages into a thread safe queue. The front end acts as a consumer, polling that query every 100 milliseconds to update the display safely. I also implemented threading log primitives around the move it commands to ensure that the robot never receives conflicting instructions during a trajectory execution. So, let's move on to a system demonstration. So, here I load up the RVs and my project file. I'm setting up the environment for a interrupt-free simulation demonstration. Just a second. And here I add my robot model. I make it into a full screen mode. I'll load up my GUI. As you can see, the robot has been loaded up with the conveys, 6 crates, and a shipping or reject container. Okay, so in my GUI, now I'll select a random crate. The robot goes and imitates the picking logic and presents it in front of the camera. As you can see, I have passed it according to the result. Next, I select crate 3. It goes again, imitates the logic, scans, and this time I fail even though the result is okay. Crate number 4. Again, I passed it. Let's see if I get any failed results. Crate number 2. Oh, it has also passed. Next, let's hope for a fail part this time. Yep, crate number 6. And here we go. It has defects, but I will still ship it. Let's see the last crate number 1. And it also has a defect, and I store it as it has been failed in the inspection. And here we go. This ends the demonstration. Finally, conclusion and future work. In conclusion, this project demonstrates how a raw Noetic, MoveIt, and Python can be combined to create a robust industrial grade application. Regarding future work and real world implementation, I propose 3 next steps. Computer vision, replacing the random defect generator with a real OpenCV or ReLO model to detect actual scratches on physical parts. Hardware development, swapping the simulation timestamp parameter for real Franka Panda drives to deploy the code on a physical hardware. Cloud analytics, integrating a SQL database to log reject rates and operator reactor reaction times, providing valuable data to the factory manager. And that's my project. Thank you for your time, and I'm happy to answer any of your questions. You can email me on my email ID. You can just search up for my name Sanjeev Godbole in the